a WikiVidi documentaries production. Don't forget to like and subscribe. Enjoy. Falcon Heavy. Falcon Heavy is a partially reusable super heavy lift launch vehicle designed and manufactured by SpaceX. It is derived from the Falcon 9 vehicle and consists of a strengthened Falcon 9 first stage as a central core with 2 additional first stages as strap-on boosters. This increases the low Earth orbit maximum payload to 63,800 kilograms, compared to for a Falcon 9 full thrust, for Delta IV Heavy. For the Space Shuttle and for Saturn V, Falcon Heavy is the world's 4th highest capacity rocket ever built, after Saturn V, Energia and N1. And the most powerful rocket in operation as of 2018. SpaceX conducted Falcon Heavy's maiden launch on February 6, 2018, at 3:45 p.m. EST. The rocket carried a Tesla Roadster belonging to SpaceX founder Elon Musk as a dummy payload. Falcon Heavy was designed to carry humans into space further than ever before, especially to the Moon, Mars, and potentially to asteroids for mining, although it is not planned to do the work necessary to obtain a U.S. government certification for the launch vehicle to carry NASA astronauts. History. Concepts for a Falcon Heavy launch vehicle were initially discussed as early as 2004. SpaceX unveiled the plan for the Falcon Heavy to the public at a Washington, D.C. news conference in April 2011, with initial test flight expected in 2013. A number of factors delayed the planned maiden flight by 5 years to 2018, including 2 anomalies with Falcon 9 launch vehicles, which required all engineering resources to be dedicated to failure analysis, halting flight operations for many months. The integration and structural challenges of combining 3 Falcon 9 cores were much more difficult than expected. In July 2017, Elon Musk said, "It actually ended up being way harder to do Falcon Heavy than we thought. Really way more difficult than we originally thought. We were pretty naive about that." The initial test flight for a Falcon Heavy lifted off on February 6, 2018, at 3:45 p.m. EST. After a 2-hour delay due to unfavorable wind conditions. Conception and funding. Musk mentioned Falcon Heavy in a September 2005 news update, referring to a customer request from 18 months prior. Various solutions using the planned Falcon 5 had been explored, but the only cost-effective, reliable iteration was one that used a 9-engine first stage, the Falcon 9. The Falcon Heavy was developed with private capital, with Musk stating that the cost was more than $500 million. No government financing was provided for its development. Design and development. The Falcon Heavy design is based on Falcon 9's fuselage and engines. By 2008, SpaceX had been aiming for the first launch of Falcon 9 in 2009, while Falcon 9 Heavy would be in a couple of years. Speaking at the 2008 Mars Society conference, Musk also indicated that he expected a hydrogen-fueled upper stage would follow 2-3 years later. By April 2011, the capabilities and performance of the Falcon 9 vehicle were better understood, SpaceX having completed 2 successful demonstration missions to LEO, one of which included reignition of the second stage engine. At a press conference at the National Press Club in Washington, D.C. on April 5, 2011, Musk stated that Falcon Heavy would carry more payload to orbit or escape velocity than any vehicle in history, apart from the Saturn V moon rocket and Soviet Energia rocket. In the same year, with the expected increase in demand for both variants, SpaceX announced plans to expand manufacturing capacity, as we build towards the capability of producing a Falcon 9 first stage or Falcon Heavy side booster every week and an upper stage every 2 weeks. In 2015, SpaceX announced a number of changes to the Falcon Heavy rocket, worked in parallel to the upgrade of the Falcon 9 V1.1 launch vehicle. In December 2016, SpaceX released a photo showing the Falcon Heavy enter stage at the company headquarters in Hawthorne, California. Testing. By May 2013, a new, partly underground test stand was being built at the SpaceX Rocket Development and Test Facility in McGregor, Texas, specifically to test the triple cores and 27 rocket engines of the Falcon Heavy. However, no triple-core tests at McGregor have occurred. By May 2017, SpaceX did the first static fire test of flight design Falcon Heavy center core at the McGregor facility. In July 2017, Musk discussed publicly the challenges of testing a complex launch vehicle like the three-cow Falcon Heavy, indicating that a large extent of the new design is really impossible to test on the ground, and could not be effectively tested independent of actual flight tests. By September 2017, all three first-stage cores had completed their static fire tests on the ground test stand. The first Falcon Heavy static fire test was conducted on January 24, 2018. Maiden flight. In April 2011, Musk was planning for a first launch of Falcon Heavy from Vandenberg Air Force Base on the West Coast in 2013. SpaceX refurbished Launch Complex 4E at Vandenberg AFB to accommodate Falcon 9 and Heavy. The first launch from the Cape Canaveral East Coast Launch Complex was planned for late 2013 or 2014. Due partly to the failure of SpaceX Res-7 in June 2015, SpaceX rescheduled the maiden Falcon Heavy flight in September 2015 to occur no earlier than April 2016, but by February 2016 had postponed it again to late 2016. The flight was to be launched from the refurbished Kennedy Space Center Launch Complex 39A. In August 2016, the demonstration flight was moved to early 2017, then to summer 2017, to late 2017 and to January 2018. Future missions were rescheduled accordingly. A second demonstration flight is currently scheduled for 2018 with the STP-2 U.S. Air Force payload. Operational GTO missions for Intelsat and Inmarsat, which were planned for late 2017, were moved to the Falcon 9 full-thrust rocket version as it became powerful enough to lift those heavy payloads in its expendable configuration. The first commercial GTO mission is also scheduled in 2018 for Arabsat. At a July 2017 meeting of the International Space Station Research and Development meeting in Washington, D.C., Musk downplayed expectations for the success of the maiden flight. "There's a real good chance the vehicle won't make it to orbit. I hope it makes it far enough away from the pad that it does not cause pad damage. I would consider even that a win, to be honest." Musk went on to say the integration and structural challenges of combining three Falcon 9 cores were much more difficult than expected. The plan was for all three cores to land back on Earth after launch. In December 2017, Musk tweeted that the dummy payload on the maiden Falcon Heavy launch would be his personal midnight cherry Tesla Roadster playing David Bowie's Life on Mars, and that it would be launched into an orbit around the Sun that will take it as far out as Mars orbit. He released pictures in the following days. The car has 3 cameras attached that provided epic views. On December 28, 2017, the Falcon Heavy was moved to the launch pad in preparation of a static fire test of all 27 engines, which was expected on January 19, 2018. However, due to the U.S. government shutdown that began on January 20, the testing and launch were further delayed. The static fire test was conducted on January 24, 2018. Musk confirmed via Twitter that the test was good, and announced the rocket would be launched in approximately 1 week. On February 6, 2018, after a delay of over 2 hours due to high winds, a successful maiden flight of the Falcon Heavy started at 3:45 p.m. EST, with its side boosters landing safely on landing zones 1 and 2. However, only one of 3 engines on the center booster ignited during its descent, causing it to hit the water next to the drone ship at a speed of over 480 km per hour. Initially, Elon Musk tweeted that the Roadster had overshot its planned heliocentric orbit, and it would reach asteroid belt, but this was, however, disproven. Design. The Heavy configuration consists of a structurally strengthened Falcon 9 as the core component, with 2 additional Falcon 9 first stages acting as liquid fuel strap-on boosters, which is conceptually similar to ELV Delta IV Heavy launcher, and proposals for the Atlas V Heavy and Russian Angar IA-5V. Falcon Heavy has more lift capability than any other operational rocket, with a payload of 64,000 kilograms to low Earth orbit and 16,800 kilograms to trans-Mars injection. The rocket was designed to meet or exceed all current requirements of human rating. The structural safety margins are 40% above flight loads, higher than the 25% margins of other rockets. Falcon Heavy was designed from the outset to carry humans into space, and it would restore the possibility of flying crewed missions to the Moon or Mars. The first stage is powered by 3 Falcon 9 derived cores, each equipped with 9 Merlin 1D engines. The Falcon Heavy has a total sea-level thrust at liftoff of 22,819 kilonewtons from the 27 Merlin 1D engines, while thrust rises to 24,681 kilonewtons as the craft climbs out of the atmosphere. The upper stage is powered by a single Merlin 1D engine modified for vacuum operation, with a thrust of 934 kilonewtons, an expansion ratio of 117:1 and a nominal burn time of 397 seconds. At launch, the center core throttles to full power for a few seconds for additional thrust, then throttles down. This allows a longer burn time. After the side boosters separate, the center core throttles back up to maximum thrust for added reliability of restart. The engine has dual redundant pyrophoric igniters. The interstage, which connects the upper and lower stage for Falcon 9, is a carbon fiber aluminum core composite structure. Stage separation occurs via reusable separation collets and a pneumatic pusher system. The Falcon 9 tank walls and domes are made from aluminium lithium alloy. SpaceX uses an all-friction stir-welded tank. The second stage tank of Falcon 9 is simply a shorter version of the first stage tank and uses most of the same tooling, material, and manufacturing techniques. This approach reduces manufacturing costs during vehicle production. All 3 cores of the Falcon Heavy arrange the engines in a structural form SpaceX calls Octor-Ebb, aimed at streamlining the manufacturing process. And each core includes 4 extensible landing legs to control the descent of the boosters and center core through the atmosphere. SpaceX uses small grid fins which deploy from the vehicle after separation. Immediately after the side boosters separate, the center engine in each burns for a few seconds in order to control the booster's trajectory safely away from the rocket. The legs then deploy as the boosters turn back to Earth, landing each softly on the ground. The center core continues to fire until stage separation, after which its legs deploy and land back on Earth on a drone ship. The landing legs are made of carbon fiber with aluminum honeycomb structure. The 4 legs stow along the sides of each core during liftoff and later extend outward and down for landing. Capabilities. The partially reusable Falcon Heavy falls into the heavy lift range of launch systems, capable of lifting 20 to 50 metric tons into low Earth orbit, under the classification system used by a NASA Human Spaceflight Review Panel. A fully expendable Falcon Heavy may also reach the super heavy lift category. The initial concept envisioned payloads of 24,750 kilograms to LEO, but by April 2011 this was projected to be up to 53,000 kilograms with GTO payloads up to 12,000 kilograms. Later reports in 2011 projected higher payloads beyond LEO, including 19,000 kilograms to geostationary transfer orbit, 16,000 kilograms to translunar trajectory, and 14,000 kilograms on a trans-Martian orbit to Mars. By late 2013, SpaceX raised the projected GTO payload for Falcon Heavy to up to 21,200 kilograms. In April 2017, the projected LEO payload for Falcon Heavy was raised from 54,400 kilograms to 63,800 kilograms. The maximum payload is achieved when the rocket flies a fully expendable launch profile, not recovering any of the 3 first-stage boosters. Reusability. From 2013 to 2016, SpaceX conducted parallel development of a reusable rocket architecture for Falcon 9 that applies to parts of Falcon Heavy as well. Early on, SpaceX had expressed hopes that all rocket stages would eventually be reusable. SpaceX has since demonstrated routine land and sea recovery of the Falcon 9 first stage, and has made attempts to recover the payload fairing. In the case of Falcon Heavy, the two outer cores separate from the rocket earlier in the flight, and are thus moving at a lower velocity than in a Falcon 9 launch profile. For the first flight of Falcon Heavy, SpaceX had considered attempting to recover the second stage, but did not execute this plan. SpaceX has indicated that the Falcon Heavy payload performance to geosynchronous transfer orbit will be reduced due to the addition of the reusable technology, but that the rocket would fly at a much lower price. When recovering all three booster cores, GTO payload is, if only the two outside cores are recovered while the center core is expended, GTO payload would be approximately. As a comparison, the next heaviest contemporary rocket, the fully expendable Delta IV Heavy, can deliver to GTO. Thus, if recovering all three cores, the Falcon Heavy can deliver only 56% as much mass to GTO as the Delta IV Heavy. But if the center core is expended, it can deliver 12% more. Propellant crossfeed. Falcon Heavy was originally designed with a unique propellant crossfeed capability, whereby the center core engines would be supplied with fuel and oxidizer from the two side cores until their separation. Operating all engines at full thrust from launch, with fuel supplied mainly from the side boosters, would deplete the side boosters sooner, allowing their earlier separation. This would in turn leave most of the center core propellant available after booster separation, with a lighter load to accelerate. The propellant crossfeed system was originally proposed in a 1998 book on orbital mechanics by Tom Logsdon, and nicknamed asparagus staging. Musk stated in 2016 that crossfeed would finally not be implemented. Instead, the center booster throttles down shortly after liftoff to conserve fuel, and resumes full thrust after the side boosters have separated. Launch prices. At an appearance in May 2004 before the United States Senate Committee on Commerce, Science, and Transportation, Musk testified, "Long-term plans call for development of a heavy lift product and even a super heavy. If there is customer demand, we expect that each size increase would result in a meaningful decrease in cost per pound orbit. Ultimately, I believe $500 per pound or less is very achievable." This $500 per pound goal stated by Musk in 2011 is 35% of the cost of the lowest cost per pound LEO-capable launch system in a circa 2000 study, for Zunit, a medium-lift launch vehicle that can carry 30,000 pounds into LEO. Falcon Heavy launch prices are below $1,000 per pound to low Earth orbit when the launch vehicle is transporting its maximum delivered cargo weight. The published prices for Falcon Heavy launches have changed somewhat from year to year, with announced prices for the various versions of Falcon Heavy priced at $80,125 million in 2011, $83,128 in 2012, $77,135 in 2013, $85 million for up to 6,400 kilograms to GTO in 2014, $90 million for up to 8,000 kilograms to GTO in 2016, and $150 million for 63,800 kilograms to LEO Oregon 26700 kg to GTO, or $95 million for 90% of its maximum capacity in 2018. Launch contracts typically reflect launch prices at the time the contract is signed. In 2011, SpaceX stated that the cost of reaching low Earth orbit could be as low as $1,000 per pound if an annual rate of 4 launches can be sustained, and as of 2011 planned to eventually launch as many as 10 Falcon Heavies and 10 Falcon 9s annually. A third launch site, intended exclusively for SpaceX private use, is planned at Boca Chica Village, Texas. SpaceX started construction on the third Falcon Heavy launch facility in 2014, with the first launches from the facility no earlier than late 2018. In late 2013, SpaceX had projected Falcon Heavy's inaugural flight to be in 2014, but it did not occur until February 2018 due to limited manufacturing capacity and the need to deliver on the Falcon 9 launch manifest. By late 2013, SpaceX prices for space launch were already the lowest in the industry. SpaceX's price for reused spacecraft could be reduced up to 30% short-term, and potentially even further in the future. First commercial contracts. In May 2012, SpaceX announced that Intelsat had signed the first commercial contract for a Falcon Heavy flight. It was not confirmed at the time when the first Intelsat launch would occur, but the agreement will have SpaceX delivering satellites to geosynchronous transfer orbit. In August 2016, it emerged that this Intelsat contract had been reassigned to a Falcon 9 full-thrust mission to deliver Intelsat 35E into orbit in the third quarter of 2017. Performance improvements of the Falcon 9 vehicle family. Since the 2012 announcement, advertising 8,300 kilograms to GTO for its expendable flight profile, enable the launch of this 6,000 kilogram satellite without upgrading to a Falcon Heavy variant. In 2014, Inmarsat booked 3 launches with Falcon Heavy, but due to delays they switched to payload to Ariane 5 for 2017. Similarly to the Intelsat 35E case, another satellite from this contract, Inmarsat 5F4, was switched to a Falcon 9 full thrust thanks to the increased liftoff capacity. The remaining contract covers the launch of Inmarsat 6F1 in 2020 on a Falcon 9. Brought to you by WikiVidi documentaries. Would you like to know more?